Spread footing design for columns. Make sure you have your Google Doc out so that you can take screenshots as necessary, and remember, typing it out helps you remember it better. It's always a better option. So what we're going to look at is we're going to look at how to calculate pressure for footings based on the soil that you have. So if we look here, we have a column that's on some sort of a pier at times, or sometimes just directly onto a spread footing. So if this is my spread footing, spread footings have thicknesses like this, and here is my column, then I have a column on a spread footing. That's what I'm going to use as kind of my demonstration when I explain some of these things. So the widened part of the foundation spreads the column load over a broader soil area. The footing is wider. You can see this has a giant area compared to the area of this little column here. So that way the column doesn't just sink into the ground. It's like a pad on a hand or a foot, so that it actually spreads and distributes that out. So breaking this down, a column load, you have all these different loads. You have the roof, floor loads, weight of the column, weight of the foundation. All of that goes down onto this footing, and hopefully the footing is big right here. The soil has a certain soil bearing pressure. It allows a certain amount of load before it actually gives, and that footing will sink into it. So you have to know what the soil bearing pressure is by doing a soil survey. You actually dig up some dirt and you figure out how much pressure can this soil hold based on what it's made out of. And once we know that number, then we can figure out how big does our footing have to be to hold this giant load. So that's what structural engineers do. So what we need to do is we need to be able to size the spread footing, and it's based on two things: the total load applied to the soil, the downward thing, and then the allowable soil bearing capacity, this upward thing. And in this case, the pressure applied due to total load has to be less than or equal to the soil bearing pressure, and I would say generally less than. You don't really want the downward load to be exactly equal to the upward, because any additional load applied to this, and then that's going to sink into the ground, and nothing's going to push it back up. You're just going to have footings that are off kilter, which is bad. All right, so add this equation, soil bearing pressure equation. Q is soil bearing pressure. It is load applied divided by area of footing. Q equals P over A. So screenshot that or type that out. And these are your soil bearing capacities. So you have this table. This is going to be in Schoology, a copy of this version. You can take a screenshot of it too. It's nice to have. So these are different soil types in sort of generic groupings here. From bedrock, which is all the way from 4,000 to 12,000, very, very poor drainage because it's rock. It's not going to be able to drain very well at all. But gravel, or gravel with fines, gravel with a little bit of silts and clays, those are fines. Fines are silt and clay. That's good drainage, and it allows 3,000 pounds per square foot, and so on and so on. So some of your worst options are silts and clay, 1,500 pounds per square feet. Medium drainage, so drainage goes down and pressure. And then organics, which would be something like tundra type ground, it's very poor, 0 to 400, poor drainage, all that kind of stuff. So in Colorado, we are generally clay, and which is medium drainage and a little bit poor soil bearing pressure. So that's something that engineers in Colorado have to deal with. So to do our calculations, to figure out your footing area, remember Q equals P over A. You just took a screenshot of that, I wrote that down. So the allowable soil bearing pressure has to be greater than that minimum Q. That's why this just says Q is greater than or equal to Q. It's kind of dumb, but that's what that means. So Q allowable, if we substitute the equation, Q is greater than P over A, greater than or equal to. If we rearrange it and solve for A, the area of the footing has to be greater than or equal to the load divided by the allowable soil bearing pressure. So this bottom equation here, that's why it's a little bit bigger, is something that we're going to end up using also. So you might want to note that down. Another equation here is the pressure for the footing equals the thickness, this T here, that thickness here, times 150 pounds per cubic foot. This is how much concrete weighs per cubic foot. So that's a constant. 150 pounds per cubic foot is always the number you're going to use. So if I have a footing here, this is the thickness of the footing, whatever that is, times 150, and that's going to give me P, that the force that the footing is applied. So remember, I have all the load of the column, the floors, the roof, everything pushing down onto the footing and into the soil, but I also had the load of the footing itself. And that's what we're finding right now. We're finding, because concrete is crazy heavy, how much load am I adding just by the footing? That's what P is. So we're going to have to add P with all of the rest of this stuff that goes onto this column. So Q net, the net load equals the Q allowable, how much soil pressure we're allowed, minus that pressure of the footing itself. So I'm going to give an example of that. It'll make a little bit more sense. A little confusing right now, but you get it. The A value here that we're solving for, it's got to be greater than or equal to that area of the load for the column divided by the net Q, which is found here. So again, we're going to go through an example to show you how this is all done. The area of the column, the required footing area, has to be greater than or equal to the column load divided by the allowable soil bearing pressure net. And remember that net means you're taking into account what the footing is actually applied to there. So let's take a look at an example here. We have a building, and remember our goal is to find the area of the footing. So the footing thickness is 1 foot 9 inches. We have to do that in feet. So in your notes, why don't you add this into there so that you can kind of follow along with us, that the footing thickness is 1.75 feet, because remember 9 inches is 0.75 of a foot. And we're going to assume the footings bear on silty gravel with a pressure of 3,000 pounds per square foot. Well, where do we get the 3,000 from? I'm going to show you. If we go back to here, you can see gravels with fine silty gravel, 3,000 pounds per square foot. So that's where we get these numbers from. So if the problem tells you it's going to be built on clays, you just go to the table and you say, oh, that's 1,500 pounds per square foot. So back at this. So we know two things right now. There's just kind of a layout of this. So remember, when you chase loads, the loads from these beams go to the girders, and then from the girders go to the columns, and then all of that goes down into the footing. So we would need to know the loads that are on the beams, then on the total on the girders, the total on the columns, to figure out how much that load is going down on the footing. So that's going to be a value that we would have to calculate. We have done a little bit of this to figure out, remember you go halfway to figure out all the loads on the girders. It's halfway from column to column. So for this example, we're just going to assume that the engineer has already done all that, and that's what I'm going to do for you. We're going to give you those values. They're giving you these masses that are applied, these loads that are applied. So it's from the roof to the second floor to the first floor, and we're going to say the roof is 10,000, interior is 20,000, second floor, and so on. So the column weight is 1,500. So the total, so this value here is 112,500 pounds. That is the total load down. So that's really the important piece. That's what I'm going to give you this information, because I don't need us to recalculate these pieces for what we're doing here. So you're going to be given that 112,500 pounds. Yeah, that's boxed right there. And now we need to calculate the net allowable soil bearing pressure. So remember from your formula, the load on the footing equals the thickness times 150. Well, the thickness was 1.75 feet, 1 foot 9 inches. So we have the pressure from this footing is 262.5 psf. We had 3,000 psf that we were allowed, so we subtract that out of there. So the net pressure is what we were allowed minus the footing. So our net is what we were allowed minus 262.5, or 2,737.5. That is our net. That's how much we can actually apply down into this footing now. So now we have to figure out what the area is from that. So remember your equation, the area is greater than or equal to the load divided by Q net. Well, we know the load. Pressure on the column divided by Q net. It was 112,500 divided by what we just solved for, 2737.5. We divide these and we're going to find what the area is. And we find it's 41.1 square feet. So that's how big our column has to be. That is the area that this shape has to be. Now you're asking yourself right now, well, what if we chose a circle or a rectangle or a perfect square? Well, then you can solve for either one of those. So a square is both sides are the same. So x squared equals 41.1. That's how we would use that. We would take this number, we'd set it equal to the formula. Or if we wanted to choose one of these dimensions, then let's say I wanted the base side to be 3 feet, then I could do 3 times h equals 41.1 and solve for h. Same thing for the circle, 41.1 equals pi r squared, solve for the radius. So we'll do one of those. If we say it's a perfect square, 41.1 equals x squared, square root that, and you get a side length of 6.4 feet. It's roughly 6.5 feet, or 6 feet 6 inches. So that's what you should use. You should always round up a little bit just to make sure that it is big enough. And remember, it was 1 foot 9 inches thick, or 1.75 feet thick. So this is your final answer for how big that square footing is going to be. Now, if you used a round footing, then you set it equal to pi r squared. So 41.4 equals pi r squared. We divide by pi to get r squared, and that is 13.1, and then square root it. And you get a radius of 3.6 feet. So 3.6 feet is roughly 3 feet 9 inches. It's a little bit less than that. So, but we're kind of rounding it up to the nearest quarter of a foot, 3.75 feet. So double that to get the diameter of 7 feet 6 inches. And again, it's 1 foot 9 inches thick. So those are both going to give you sizes that are big enough so that when you put your column and your load all the way on there, it doesn't sink into the ground. The soil bearing pressure that's pushing up on it is enough to support the downward force. That's our goal. Now it's your turn to try the practice problems that are attached to next in Schoology. Good luck.